the general launch angle, where the projectile is launched at an angle Earlier we discussed the zero launch angle, where the projectile was launched horizontally. Now we'll discuss the general launch angle, where the projectile is launched at an angle arbitrary with respect to horizontal. Like this, projectile is launched at an angle theta above the horizontal. So we'll discuss this case. So let the projectile is launched with a velocity of v0 at an angle theta above the x-axis, and we have taken this as our coordinate system. There's a positive x, there's a positive y, and initially the projectile is at the origin, so x0 will be 0 and y0 will also be 0, and during the motion the only acceleration on the projectile is the acceleration due to gravity, which is ay, because it's along the negative y. So that is why we can write ay is minus g. Now this velocity will have two components in the x and the y direction. In the x direction we have, this is v0 x, which will be equals to v0 cosine theta, and in the y direction we will have v0 y, which will be equals to v0 sine theta, right? Now we're going to substitute all these values in the basic equations for the projectile motion. So first I'll apply these values in the horizontal direction. Since it's a projectile motion, so we can study the motion separately in the x direction and in the y direction, right? So first will we see the basic equation in the x direction. So in the x direction we have x is equals to x0 plus v0 x times t plus 1 over 2 ax t square. This is position as a function of time. Now x0 we have 0, so this whole term is 0. Ax, there is no acceleration in the x direction, so ax is 0, so this whole term will be 0, right? So we'll obtain that x is equals to, now v0 x we have v0 cosine theta multiplied with t. So this equation tells us the position of the projectile at any given time t. So this is the first equation of motion for this case. Now we'll see position as a function of time in the y direction. So we have y is equals to y0 plus v0 y times t plus 1 over 2 times ay times t square, right? Now initially the position is at origin, so y0 is 0. v0 y we have v0 sine theta multiplied with time t plus 1 over 2. Now ay we have minus g t square. So from here we'll get y is equals to v0 sine theta multiplied with t minus 1 over 2 g t square. So this is the second equation. Now we'll see velocity as a function of time in x and y direction. So in x direction we have vx is equals to v0 x plus axt. Now there is no acceleration in the x direction, so this whole term is 0. So vx will be equals to v0 x, and v0 x we have v0 cosine theta, right? Similarly in the y direction we have vy is equals to v0 y plus ay times t. So vy, this will be equals to v0 sine theta minus gt, because ay we have g minus g, so minus gt. So this is the third and the fourth equation. Now we'll see position as a function of velocity in x and y direction. So in the x direction we have vx square is equals to v0 x square plus 2ax times delta x. There is no acceleration in x, so this is 0. So vx square will be equals to v0 x we have v0 cosine theta and its whole square, so that would be vx square is equals to v0 square cosine square theta, right? This is our fifth equation, and the final one in the y direction we have Vy square is equals to V naught square sine square theta. Then we have 2 Ay delta y this time. So this would be minus 2g delta y, because this time this would be replaced by Ay, and Ay we have minus g, so that is why minus 2g, and this delta x will be replaced by delta y. So this is the final equation of motion for this case. Now we'll take an example on zero launch angle. So this is our example, and it says that a projectile is launched from the origin with an initial speed of 20 meter per second at an angle 35 degrees above the horizontal. So let me first draw the coordinate system. So these are coordinate system. This is the positive x and this is the positive y. Now the projectile is launched at an angle 35 degrees above the horizontal. So this is the direction of the velocity, and this angle is 35 degrees, and the velocity v naught we have 20.0 meter per second. Now there are two parts in this question that we need to solve. First we're going to solve the A part. In the A part we need to find the x and y positions of the projectile at time t equals to 0.500 seconds. So we have to use the equation position as a function of time in x and y direction respectively. So to solve the A part, I'm going to use these two equations, this one and this one. So we can write that x is equals to v naught cosine theta times t, because if you see the component of velocity in the x direction, this will be v naught x, this will be v naught cosine theta. Similarly in the y direction we have the component v naught sine theta. And if you don't know how to take the components, you better see my previous videos in the third chapter, where I discussed the components of a vector. Now we're going to put the values. So v naught we have 20.0 meter per second times cosine theta is 35 degree multiplied with time we have to take to be 0.500 seconds, and on further solving we'll get this value to be 8.19 meter. So this will be the position of the projectile at this time. Now next we have to find the y coordinate. So for that I'm going to use y is equals to v naught sine theta times t minus 1 over 2 gt square. This is the same equation, second equation that we derived just now. Now I'm going to put the values. So this is v naught is 20.0, sine theta is 35 degrees multiplied with time is 0.5, minus 1 over 2, g is 9.81, and time is 0.5. Now we have plugged all the values in SI unit, so we'll get the answer in the SI unit. So we'll get this value to be in meters, 4.51 meter. So this will be the y coordinate and the answer for the A part, right? Now next in the B part we need to find the velocity of the projectile at time t equals to 0.500 seconds. So for this we're going to use the velocity as a function of time. Let me first show it also that we derived earlier. This is the velocity as a function of time. So these two equations I'm going to use. So we have, this is the B part, we have Vx is equals to V naught cosine theta. We can put the values. V naught we have 20.0 meter per second, cosine theta is 35 degrees, and on further solving we'll get this value to be 16.4 meter per second. So this is the Vx. Similarly Vy, this will be equals to V naught sine theta minus gt. V naught we have 20.0 meter per second, sine theta is 35 degrees minus g is 9.81, multiplied with time is 0.5 seconds, and on further solving we'll get this value of Vy to be equals to 6.57 meter per second. So this is the speed of the projectile in the x direction at time t equals to 0.5 seconds. Similarly, this is the speed of the projectile in the y direction at time t equals to 0.5 seconds. Now we can represent it in the vector form. So the velocity vector will be equals to the x component, which is 16.4 meter per second, and the unit vector will be x cap, plus this will be 6.57 meter per second, and the unit vector is y cap. So this is a vector representation of the velocity. Now you have to repeat this problem for time t equals to 1 seconds. Here we have took time t equals to 0.5 seconds, but you have to repeat the problem for time t equals to 1 seconds. I'm just writing the answer so that you can compare whether you have got the right answers or not. So at time t equals to 1, the x value would be 16.4 meter, this is x position, and the y coordinate will be 6.57 meter. And the velocity vector at time t equals to 1 will look something like that: 16.4 meter per second x cap plus 1.66 meter per second y cap. So these are the answers. You can compare it. If you have any problem, you can comment me in the comment box below. Now we're going to plot the trajectory of the projectile. So this is the trajectory of the projectile, and the position shown in the plot corresponds to the time t equals to 0.1 seconds, then 0.2 seconds, then 0.3 seconds, and so on. Like here, this is the position of the projectile at time t equals to 0.1 second. This will be the x coordinate, this will be the y coordinate. Similarly, this is the position of the projectile at time t equals to 0.2 seconds, and so on. Let me represent, this is the y-axis and this is the x-axis. Right. Now if you observe this plot carefully, we see that the points are not evenly spaced in terms of position, even though they are evenly spaced in time. Like here, the points are much closer, and here the points are much wider. Therefore we can say that large fraction of time is spent near the highest point and least fraction of time is spent initially. And this is the reason it seems that the basket player rise very fast towards the slam dunk, as you can see in this video. So this is all happening because of the laws of physics that we studied just now. So this is all with this video, and in the next video we'll see few more examples on general launch angle.